All right, this video's, I started the video while sirens were going off, but that's okay. Probably after watching the last video, their brain exploded. But okay, so this video is going to be on solving differential equations using sums, using power series. And okay, so normally when doing differential equations, the easiest way to solve them is to plug in like x equals, let's not do x, let's do like u equals e to the kx, and then plug that in, solve for k, and then get your answer in the form of like a sine kx plus b cos kx. Like get something like that, right? That's typically the easiest way to solve them. However, there are some differential equations where you need to solve them using a power series. And this was taught in like the first, what's it called? The first class towards your master's. And I got my master's and I've never had to use this. But I'm sure there is a use for this somewhere out there. But okay. Cool. So let's say you have this differential equation, 2x d squared y over dx squared. All right, let's say that's your differential equation. Cool. So, step one, we have to see which type of power series we can use to solve this. And is it even possible to solve it using a power series? There are two types of power series. There's a normal one, and then there's a Frobenius. And there's a couple checks that you do to see whether first you can solve it, whether you can solve it with the normal one, and whether you can solve it with Frobenius. And you do it in that order. So before you even do that though, you need to write this in standard form. Standard form. That is so all I did was literally just divided by that 2x. Cool, and this lets you say this term is called A1, and this term is called A2. Well, you can call it whatever you want, but that's how I called it. So, step one is to ask whether there's a singular point, whether either of these terms are undefined. And they're undefined whenever you divide by 0. So in both of these cases, you have an undefined point at x equals 0. So let's just leave that there for a second. Okay. So step one, let's see if this is an irregular singular point. Basically, can we even solve it? So the checks for that are if the limit, these are going to be kind of weird, but this is the process. So it's going to be whether the limit of that goes to infinity or I think it's or. It is or. goes to infinity. And to be honest, if you just thought about it, you could come up with these checks, but don't worry about that. All right, so this first one, limit is x minus x naught, so that would just be x minus 0 times a1 goes to infinity when you plug in 0 into x. So this equals 1 plus x over 2, because that x cancels out. And if you plug in 0, you get 1/2, which doesn't equal infinity. So that check fails. Here we have, it's going to be x minus 0, so I'm just going to call it x squared times a2, which is 1 over 2x, which equals x over 2. We plug in 0, and we get 0, which doesn't equal infinity. So can we solve it? Yes. Okay, so it passes, well, it fails a test to see if we can't solve it. Cool. So now we see if we can solve it using a singular point method. And the checks for that are that looks ugly. I'll explain what singular point means in a second, but the checks for that are or okay. So a1 of x, 1 plus x over 2x, plug in 0, and we get infinity. So this is a pass. And same here. Yeah, because it'll be 1 over 2x. 2x, which equals infinity, so pass. That doesn't look like a yes at all. But it passes a singular point test, which means that we can solve it using power series that looks like it's a sum from 0 to infinity of ak, which we'll have to solve for, times x to the power of k. So this will look like a1 x to the 0, which is 1, plus a2 x. No, it would be, what would it be? There's a0 first. a0 x to the 0, which is 1, plus a1 x to the 1, plus a2x squared, and so on. So we could solve it with this method, but we also have to check if we can solve it with Frobenius. And if we can solve it with Frobenius, we choose Frobenius over this method. Okay, so Frobenius, the check is called regular singular. These two conditions were or. This condition is and, so both of these have to be true. No, it said equal infinity also. Okay, so this first one, it'll be x minus 0, so I'm going to just call it x, times a1. 1 plus x over 2x. So this will equal 2, and we plug in 0, and we get 1/2, which doesn't equal infinity, which is a pass. Second one, we have x squared times a2, 1 over 2x, which equals x over 2. We plug in 0, we get 0, which doesn't equal infinity. Pass. Yeah. Unfortunately, Frobenius sucks more than this regular method, and the Frobenius method is k plus s, where here it was just k. And that is because there isn't just a singular point. There are multiple points, multiple solution points, and you have to account for that by adding s. This whole method, the whole problem-solving method that we're going to do, the concepts are very easy. The math, it's a lot of algebra, and you can mess up very, very easily. And adding another term to the exponent just makes you more likely to mess up. So you got to be super careful. Okay, so we're going to solve this differential equation using the Frobenius method, unfortunately. So to do that, all right, we have y equals that. We need the derivative of y, and we need the second derivative of y. So let's write all of that out. Let's just write it out down here. Let's write out everything again. All right, that's our equation. And let's write out all of these. So we have y equals sum from 0 to infinity. And then we have y prime equals 0 to infinity. AK, you multiply the k plus s down, and you have x, k plus s minus 1. Yep, and then y double prime is 0 to infinity. AK, k plus s, k plus s minus 1, x, k plus s minus 2. Already that looks like it sucks, and it does. Before you even go any further, I'm going to say, if you're asked, well, if the regular singular test fails and you have to solve it using the normal standard power series method with this equation, instead of the Frobenius, it's literally these exact same steps that I'm doing right here. Except there's no plus s. So like, for example, this derivative would be ak. So you wouldn't have that there. So you'd just have a k, x, k minus 1. That would literally be it. That's like the only difference. all the steps are exactly the same. But I just chose a problem that has Frobenius because it is the more complicated one, as in more algebra, so might as well just do it. I'm going to do it once, might as well make it as bad as possible. Okay, so now we plug all of this stuff in, and we get 2x I don't even need the parentheses. Yep. I'm going to multiply this out to each of them. So I've got a 1 times the derivative of y. So it's just going to be 1 times all of that, but I'm just not going to write the 1. And then we have x times that same thing. And then we have just a y at the end. Equals 0. Okay, so step 1, plug in. Doesn't seem that bad. Just double checking that I didn't miss anything. I think I'm good. All right, step 2, multiply in all of the x's that we have. And we can multiply in like this 2 as well, I guess. Yeah. Yeah, let's do that too. So if you multiply x to the 1 times x to the k plus s minus 2, you'll end up with k plus s minus 1. That's all I did there. Plus, the second term stays the same. Third term, we multiply in this x, so it should go to just k plus s. And then this last term, cool. I think that's right. Yeah, it seems right. Multiply in the x. All right, step 3. This is all just very easy math steps, but the algebra, there's a lot of algebra to keep track of. All right, step 3 is combine like terms. More specifically, these first 2 terms are alike because they sum over the same range and they have x to the same power. And these second 2 terms are alike because they sum over the same range and they have x to the same power. Okay. So yeah, we literally just sum them. yeah, that makes sense. It's that plus that, and then you just bring the k plus s minus 1 to the outside. That's what I have. I think so. Yep, that looks like exactly what I have. Okay. And then this one. Cool beans. And then the next step is to match the x power to the lowest x power. I'll write it down and then I'll explain what that means. So this is k plus s minus 1. This is k plus s. So the lower power is k plus s minus 1. So we have to write this as a k plus s minus 1. So how do we do that? Well, first, this whole first term will stay the same. So let's just rewrite that. Okay, second term. Yeah, okay. So the way we could do that is we can rewrite this, we can shift this whole sum over. And the way we do that is we go 1 to infinity. Instead of 0 to infinity, we go 1 to infinity. A k minus 1, so we're shifting a over, we're shifting this over, k plus s minus 1, plus a k minus 1, x k plus s minus 1. Cool. Cool beans. This is being able to do that. That's probably the hardest part of this whole problem. Well, it's one of the hardest parts. Being able to reindex the sum. But it's effectively the same thing, because if you plug in 1 into there, you get, this is a0, this is effectively, this will become just k plus s, this will become a0. So it's the same thing. It's just rewriting the sum so that you can rewrite the index so that these indexes match. Okay. Match x to the lowest power. We did that. Next step, write out the required sums such that these two sums are the same index. So we matched these. Now we're trying to match those without changing these exponents. So how do we do that? Well, this is literally an infinite sum. We could write out all of those terms from 0 to infinity, but that takes too long. So what we could do is write out the required sums. So for this one, it would be so we plug in 0 for k and we write it out. Is that right? That is right. Okay. And then, so that's term 1. And then we could write the rest of it as just 1 to infinity. and it'll be literally the exact same thing. But now instead of 0 to infinity, it's 1 to infinity. And this whole term stays the same as well. Is that the longest line so far? Yeah, it is, but I've written bigger every line. My font's gotten bigger, so. Okay, good news is now these two terms have the same sum index and the same x power index, so we can combine them. But before I do that, we gotta state something here. So in this step, every a term, we say it has to be arbitrary. In this one, we only have a0. So a0 and we'll see later why that's important. It's important because a1, a2, a3, a4, all the rest of the a's are a function of a0. They're not explicit, kind of. But yeah, a0 has to be arbitrary. If we had multiple a's, like if we had a0 in here plus as plus a1, then we would have to say a0 and a1 has to be arbitrary. We would say that both of them have to be arbitrary. But since we only have a0, then we're good. A way that we would have an a1 as well is if this sum had to be rewritten as 2 to infinity. Then we would have to write out the a0 term and the a1 term. But in our case, all we had to do was write out the first term. So a0 has to be arbitrary. And a0 can't equal 0. So that means that the rest of this has to equal 0. And the way that'll work, 2s minus 1 plus s equals 0. So s has to equal 0 or, what would it be? 1/2? Yeah, it is 1/2. S has to equal 0 or 1/2. So those are our two solutions for s. But okay. So now let's combine these. Let's do that right here. It's gonna be a big thing. Okay. I think that's right. That's probably right. Okay, so the only way I don't know if they taught it in this class or not. They might have just said assume it. But the only way that the sum of something can be 0 is if this inner part equals 0. So we can literally break it out. See, this inner part has to equal 0. Cool. So, but now we have two cases. We have a case where s equals 0 and where s equals 1/2. Let's do probably the s equals 0 one's easier. Dang it, I lost it. Give me a second. I lost my answer key. Here we go. Okay, yeah, let's do the s equals 0 one first. So if s equals 0, we plug s equals 0 into this equation, and we should get is that what we got? I'm double checking it. I think that's what we got. I think that's right. Okay. Now we have to solve for AK equals something times AK minus 1. We have to solve it in that form. And I'm just going to skip to it. But it's literally just algebra. AK equals negative AK minus 1 over 2K minus 1 plus 1. Cool. So for this case, that means, let's say, all right, so A0 is arbitrary. So A1 equals negative A0 over 2 times 1 minus 1 plus 1, which equals it'll be 0, so it'll be negative A0. And then A2 equals negative A1 over 2 times 2 minus 1 plus 1, which equals, and we also plug this in, so we'll have a positive A0 over 3? I think 3. Cool. And then A3 equals so on. And it's a function of A0. A4 is also a function of A0. All of them are functions of A0. well, each of them is a function of the previous one, and you have to derive the previous one and so on. So they're all functions of a0 effectively. I'm gonna just say a3 dot dot dot. So that's the s equals 0 case. The s equals 1/2 case is exactly the same process. We write out this equation and we plug in s equals 1/2. When we do that, we get I think I did some algebra between this equation and this equation, but that's fine. We get our AK equation as negative AK minus 1 over 2K minus 1/2 plus 1. So very similar to up here, except up here we had minus 1. Down here we have minus 1/2. Okay. And then exact same method as up here. Plug in a1, a1 equals negative a0, because k minus 1, or 1 minus 1 is 0, over 2 times negative 1/2 plus 1. What would that be? Actually, that would be no, it would be 1 minus 1/2. I was like, that equals 0 on the bottom, and we can't have that because we already took care of our singularity points up here, where we said x equals 0. Yeah. I was like, we can't have that. We already went around that. This equals, I don't really care what it equals, but it equals something. And then I guess to write out your final solution, since we assumed y equals sum of this times ks, our solution would be y equals sum 0 to infinity ak xk plus s, which is sum 0 to infinity ak xk plus 0 for the s equals 0 case, plus sum of 0 to infinity k plus 1/2 for the 1/2 case. And this would equal, well, we already did some of these here. So it would be a0 times negative 1 plus 1/3 plus so on, plus a0 times whatever it is, and then a2 equals whatever it is, and so on. I think that's the solution. I don't think this has to be a different a. I think that's fine. Yeah, okay. So that is the solution. And it's nice because you can multiply a0 out of all of them. And it makes sense that we would have, actually, this might have to be like B0 or something. B0. I think it does. And then like down here we would say BK, this would be BK minus 1. I think that's right. And the reason why I think that is because our differential equation had a second derivative, which means we should have two constants, a and a b, in our solution form. And we have, this is one constant, and this has to be a different constant, I think. But what are our boundary conditions? We don't have boundary conditions, so we can't solve for them, which is why we can't solve for A0 and B0. Okay. But our thing isn't even a function of x. So where does x come in? Oh, I know where it comes in. I know exactly where it comes in. Negative x to the 0, which is 1, plus x squared over 3. No, I think it would just be x over 3. So the x's are going to show up in these sums because I forgot to write this part out. I only wrote out the AK, but it's multiplied by x. Cool. Okay. That is a full Frobenius problem. And again, the only difference between Frobenius and the normal summation is you're not going to have the plus s, which means all of these steps are going to be the same. The only thing is you're not going to have to do that, which means you're not going to have two cases. You're only going to have one case. And you just solve for one case. There's no second case, but that's it. That is literally it. Cool beans.